Imagine a computer vision model that doesn't just see the world, but sees it instantly stripping away all the clutter to make decisions faster than you can blink. That isn't sci-fi, it's the new edge-first reality of YOLO26. Welcome to our podcast, Artificial Intelligence, Papers and Concepts curated by Dr. Satya Malik. Now, before we really jump into the deep end today, I do want to clarify something right off the bat, just so we're all on the same page. Both myself and my co-host here are 100% AI generated, where voices synthesized to guide you through the latest research, but every fact, every figure we discuss, it comes directly from the source material.
That's right. We're here to analyze the data, not hallucinate it. And today we have a pretty significant document to unpack. We're looking at YOLO26, key architectural enhancements and performance benchmarking for real-time object detection. This paper just came out January 16, 2026 from Sapkota and colleagues.
And it feels like, honestly, we talk about a new YOLO model every other week. The You Only Look Once family has more sequels than, like, a superhero franchise at this point. We've had V5, V8, V10, V11. Is this just another incremental version number, or is there something actually substantial here?
It's a fair question. I mean, usually the progression, let's say looking back at the jump from V12 to V13, was all about architectural complexity. The goal was, add more layers, crank up the parameter count, and try to squeeze out maybe 0.5% better accuracy.
Right, the whole bigger is better mentality.
Exactly. But YOLO26, which was first shown off by Ultralytics in London back in September 2025, it represents a real philosophical pivot. The paper explicitly states they're moving away from just chasing accuracy and are focusing on simplicity, efficiency, and innovation. It's purpose-built for the edge.
So they're not trying to win a contest on some massive H100 GPU server farm.
No, not at all. They're trying to win on a robot or a drone or your phone, places where battery life is finite and, latency can actually be dangerous.
That makes a ton of sense. On a server, a 50 millisecond delay is, a slow-loading web page? But on a self-driving car, 50 milliseconds is the difference between avoiding an obstacle and hitting it.
Precisely. So in this deep dive, we're going to look at exactly how they strip this model down to make it faster, safer, and maybe surprisingly, a lot easier to train.
Okay, but before we get into the engineering of how they got that speed, and I really want to get into the details of this NMS removal, we do need to pay the bills. This podcast is sponsored by BigVision.ai, a consulting and product development company that helps companies of all sizes build computer vision and AI solutions. You can reach them at contact@bigvision.ai. All right, let's get into the mechanics. To really get why YOLO26 is so different, we have to look at the bottleneck it claims to solve. The paper makes a huge deal about removing something called NMS.
Right, non-maximum suppression.
Okay, so for our listeners who use these models but maybe don't code the back end, walk us through why NMS was even there in the first place. It sounds kind of like a bureaucratic step.
In a way, it is. Historically, object detection models are, let's say they're very enthusiastic but not very precise. If you show a standard model an image of a single cat, it doesn't just predict one box. It gets excited. It predicts hundreds.
Hundreds.
Oh, yeah. It'll put a box on a cat's head, another on the body, one slightly to the left. It's basically hedging its bets.
So it's like throwing a handful of darts at the bullseye, just hoping one of them sticks perfectly.
That is a perfect analogy. And NMS is the referee that steps in after the darts are thrown. It looks at all those overlapping boxes, compares their confidence scores, and suppresses, or deletes, the ones that aren't the maximum. It filters the noise until one best box is left.
That sounds logical. If it works, what's the problem? Why get rid of it?
The problem is that it's a post-processing step. It happens after the neural network is done. It takes up CPU time. And crucially, the time it takes to run depends on how cluttered the scene is.
So the processing time isn't consistent?
No, not at all. If the scene is empty, NMS is fast. If the scene is crowded with objects, NMS is slow. And in control theory, for robotics variance is the enemy. You can't have a control loop where one frame takes 10 milliseconds and the next takes 40. That causes jitter.
I see. It's like trying to drive a car, but your steering wheel reacts at random intervals, sometimes instantly, sometimes with a lag.
Exactly. Smooth automation becomes impossible. So YOLO26 solves this by introducing what they call end-to-end NMS-free inference. They redesign the architecture so the network natively predicts only the correct boxes.
Wait, how do you even do that? If it's used to throwing all those darts, how do you force it to throw just one?
It comes down to the training loss, the penalty system you use to teach the AI. In older versions, the model wasn't penalized that heavily for near misses or duplicates. In YOLO26, they use a one-to-one matching strategy during training. They force the model to associate one object with exactly one prediction.
Oh, so it learns self-discipline.
Effectively, yes. If it predicts a duplicate, it gets punished. And the performance gains are massive. The paper highlights that for the nano model, the smallest one, for microcontrollers, removing NMS results in up to 43% faster CPU inference.
43%? That's not a rounding error. That's a huge leap for hardware like a Raspberry Pi.
And it removes the need for threshold tuning. You used to have to manually set this IOU threshold, basically deciding how much overlap was okay. If you set it wrong, you either got ghost objects or missed real ones. YOLO26 just eliminates that parameter. Just works.
That's a massive quality of life improvement. But NMS wasn't the only thing they cut, was it? The paper also talks a lot about removing DFL, or distribution focal loss. This sounds a bit more esoteric.
It's deeper in the math, for sure, but the impact is very practical. In models like YOLO8 and V11, they use do-FL to boost accuracy. The idea was that the edge of an object isn't always sharp, it can be blurry. So instead of predicting a hard coordinate, the model predicted a probability distribution.
You mean it would say something like, the edge is 80% likely to be at pixel 100 and 20% likely to be at pixel 101.
Exactly that. It's a soft prediction. Mathematically, it helps the model learn better because it captures uncertainty, but computationally, it's a headache for edge devices.
Why? Is the math too hard for a phone to handle?
Not impossible, no, but the operations are complex. To calculate that probability distribution, you need things like softmax and convolutions that aren't always optimized on, the neural processing units, the NPUs.
Ah, I see. So if I'm trying to export this model to run on a specific chip, like in a security camera,
The chip might look at that DFL code and say, I don't want to do this fast, and fall back to the slow CPU. It breaks the whole acceleration pipeline. YOLO26 just rips it out and goes back to a simple regression task. It just predicts the coordinates directly.
but doesn't that hurt accuracy? I mean, DFL must have been added for a reason.
There's a microscopic trade-off, yes, but because of other enhancements we can get into, the overall accuracy stays high. The benefit, though, is the model becomes hardware-friendly. It exports to ONNX, TensorArt, CoreML, and so on seamlessly. It just uses standard building blocks that every chip supports.
So it's the difference between writing a novel in standard English versus, I don't know, using some local slang that only a few people get. Standardizing makes it portable.
That's a great way to put it.
Yeah.
And this leads directly to their next big point, deployment robustness, specifically quantization.
Quantization, that's when we compress the model, right? Going from like 32-bit numbers down to 8-bit integers to make the file smaller.
Correct. It's like lowering an image's resolution to save space. Now, a lot of recent models, especially the transformer-based ones like RTD, ETR, are really fragile here. Transformers rely on these attention mechanisms that need high numerical precision. If you swash them down to 8-bit integers, their accuracy just falls off a cliff.
So they basically get dumb once you try to compress them for a phone.
They do. You can lose 5, even 10% accuracy. But because YOLO26 is a CNN, a convolutional neural network, and because they remove that complex DFL math, it's incredibly robust. You can compress it to INT8 or FP16, and the accuracy barely budges.
And that's critical for mobile apps. No one wants to download a 500 megabyte model for a parking app. They want the 20 megabyte version.
Exactly. It sets a new bar for what we call deployment robustness. It's not just about how good it is in the lab. It's about how good it is after you've shrunk it down for a $5 chip.
I want to shift gears to the training side of things, because reading this paper, I felt like I was reading like a crossover episode between computer vision and LLMs.
It certainly feels that way. The optimization strategy for YOLO26 borrows heavily from the text generation world. They introduced a new optimizer they're calling MustGD.
MustGD. Okay, break that down for us.
It's a hybrid of SGD, stochastic gradient descent, and something called muon. Now, FGD is the classic workhorse of vision training. It's reliable, but it can be slow. It sort of zigzags its way down to find the best solution. Muon is a technique that's been getting popular for training large language models. They even reference the Kimi K2 model. It doesn't just look at the slope of the hill, it looks at the curvature. It's a more advanced way of navigating.
Okay, let's try a layman's analogy on that one.
Think of SGD as walking down a hill in the fog, just feeling the ground with your feet. Muon is like having a topographic map and a compass. You see the path much more clearly, so you can take bigger, more confident steps.
So why haven't we always used this for vision?
It's computationally expensive, very memory hungry, but MostGD blends them. It uses the heavy lifting of Muon for the really critical parts and the efficiency of SGD for the rest.
And the payoff is speed.
The speed of learning. The model converges faster. You need fewer epochs, fewer runs through your data to get it to the same level of intelligence. And it stabilizes the training so it doesn't get stuck in bad habits.
Speaking of bad habits, one of the biggest issues is always the small object problem. Models are great at spotting a car, but completely miss a tiny pedestrian next to it.
Oh, that's the Achilles heel. It's a pixel real estate problem. In a 4K image, a truck might take up 1 million pixels. A drone at 400 feet might take up 20.
So during training, the model just ignores the drone because the error signal is so tiny.
Exactly. The penalty for missing the drone is drowned out. YOLO26 attacks this with 2 new things, prog loss and stale.
Prog loss, progressive loss balancing.
You got it. Think of it like dynamic difficulty in a video game. At the beginning of training, the model doesn't know anything, so all errors are treated about the same. But as it gets smarter, prog loss starts changing the weights. It forces the model to stop memorizing easy stuff and focus on the harder, smaller cases.
And stale.
Small target-aware label assignment. It's a mouthful, but it's brilliant. It explicitly prioritizes those tiny or blocked objects. It basically draws a big red circle around the small dots and tells the model, hey, this 10-pixel blob is the most important thing here. Don't ignore it.
I can see that being crucial for, say, agricultural drones scanning a field for tiny weeds or pests.
Or in manufacturing, looking for a tiny scratch on a microchip. The paper shows this combination gives YOLO26 a huge accuracy boost on datasets, lots of small objects like aerial imagery. It's closing the gap between seeing the forest and seeing the leaves.
Okay, so recapping. We've got a model that doesn't need a manager to filter its predictions. It's mathematically simpler, so it runs on any hardware. And it learns using advanced LLM math to spot tiny details.
That covers the how. Now we should probably talk about the what.
Right, the capabilities. The paper calls it a multitask framework. That sounds a little like marketing speak.
Not quite like this. Usually if you want to do different things, like detect a car versus outlining its exact shape, you need different model architectures. YOLO26 uses a unified backbone. The core engine is the same, only the final output layer, the head, changes.
And it supports 5 distinct tasks. Run us through them.
Okay, first, your standard object detection drawing the box. Second, instant segmentation.
That's where we color in the pixels of the object, right?
Yep. Exactly. It's crucial for robotics. A robot arm needs to know exactly where an object ends to grasp it. A box isn't enough. Third is posing key points, so tracking the human skeleton or the joints of a machine. Fourth is just classification. And fifth, and this one's really important, oriented detection, or OBB.
OB.
Oriented bounding boxes. Standard models draw rectangles that are upright, parallel to the screen.
Which works fine for a standing person.
But it fails for a ship seen from a satellite, or a pen lying diagonally on a desk. An upright box around a diagonal pen is mostly empty space.
Yeah.
OBB draws a rotated box that fits the object perfectly.
So for aerial maps or conveyor belts where things are just tossed around, OBB is the only way to get real precision.
Exactly. And the efficiency gain is that all 5 of these tasks share that same optimized NMS-free backbone. So if you need to do detection A and D pose estimation, you don't need 2 heavy models. You just need YOLO26.
Which brings us right back to the memory constraints on edge devices. If one model can do 3 jobs, you've just tripled your efficiency.
And that's why this paper is so focused on industrial applications. Let's, connect this to a listener who might be running a factory. Why should they switch to YOLO26 tomorrow?
Is it just about the speed?
It's about the predictability of the speed. We talked about latency variance. On an assembly line, if your vision system has hiccups because NMS took too long on a cluttered frame, you miss a defect. The product ships, and now you have a recall.
So the consistency of YOLO26 is basically an insurance policy.
Correct. And for robotics, it means a stable control loop. If a robot needs to catch a ball, the delay between seeing and acting must be minimal and constant. YOLO26 brings that latency down to a level where human-like reaction times are possible on cheap hardware.
And by cheap hardware, we mean no cloud connection needed.
No cloud, no Wi-Fi latency, no privacy risks from sending video to a server. You wrote it on a Jetson Orin, a Raspberry Pi, or a good smartphone. The data never leaves the device.
It really feels like we're hitting a maturity point. For years, computer vision was about, can we even do this? Now it feels like it's about, can we do it cheaply, reliably, and everywhere?
I'd agree with that. We're not just chasing higher numbers on a leaderboard anymore. We're chasing usability. We're moving from science project to infrastructure.
And if you're listening to this and thinking, I want to build that drone or I want to optimize that factory line, you're going to need the skills to actually implement it. If you want to get started in computer vision and AI yourself, we urge you to enroll in opencv.org/university.
Okay, we're coming to the end of our deep dive. Let's try to distill this whole thing down. What are the big 3 takeaways here?
First, I'd say speed through consistency. The NMS-free inference gets rid of that post-processing step. It speeds things up by over 40% on small devices, but more importantly, it makes the latency stable. No more jitter.
Simplicity in deployment. Getting rid of distribution focal loss, the GFL, made the model mathematically simple. It just exports cleanly to any hardware, and it handles quantization without breaking a sweat.
And third,
smarter training. By borrowing must-GD from the LLM world and using prog loss to focus on the hard stuff, the model learns faster and, critically, stops ignoring small objects.
It's a really compelling package, leaner, meaner, and smarter.
It is. And if I could leave you with one final thought, we're seeing this blurring of lines between different AI fields, borrowing math from LLMs to train vision models. If YOLO26 can see this fast and this accurately on a cheap edge device, are we approaching a point where blind spots in automation just cease to exist?
That is a thought to chew on. Can we make machines that are truly all-seeing? Thank you so much for joining us on this deep dive into YOLO26. If you enjoyed this breakdown, please make sure to subscribe so you don't miss our next exploration.
Until next time.
Goodbye.